What if the universe sent us a riddle written in a language we have yet to decipher? Not a signal, not a broadcast, but a physical object. A messenger from an unknown shore hurtling through the silent black gulfs between the stars, carrying with it a truth that threatens to shatter our most fundamental cosmic laws. For millennia, we have stared into the abyss convinced we understood the basic rules of the game: heat and cold, cause and effect. The predictable physics of a universe governed by elegant, unbreakable equations. We learned that to approach a fire is to feel its warmth. It is the first lesson of a child and the last lesson of a star. Yet out there in the fathomless dark, a visitor was coming, a traveler that would hold that simple lesson in contempt and force us to question the very nature of reality itself. Before we can meet this enigma, you must first feel the place from which it was born. Journey with us beyond the furthest whisper of our sun's influence, past the icy graveyard of the Oort Cloud and into the true void. This is interstellar space, a realm of such profound emptiness, it defies human comprehension. The silence here is absolute, a pressure of nothingness that has reigned for billions of years. The cold is a primal force, a near-perfect zero on the thermodynamic scale where the motion of atoms almost ceases. For light year upon light year, there is only the thin, cold mist of hydrogen atoms adrift and alone. Stars are not neighbours here. They are distant, solitary lighthouses separated by an ocean of unimaginable scale. To cross this ocean is a journey of millions of years, a pilgrimage of cosmic patience endured in a state of frozen hibernation. Anything that makes this crossing is not merely an object. It is a survivor, a relic, a time capsule from a place we will never see. For most of human history, the idea of a visitor from another star system was pure fantasy. Our solar system was a walled garden, a closed and isolated family of planets, moons, and comets, all born from the same spinning nebula of gas and dust. Everything we studied, from the frozen methane on Pluto to the iron heart of Mercury, was a piece of ourselves, a chapter in our own local history. But the universe, it turns out, is not so tidy. The gardens have no walls. Very rarely, once a century, perhaps once a millennium, something gets thrown. A gravitational scuffle between alien worlds, a close pass by a wandering star, and a small frozen body can be violently ejected from its home system, cast out into the great emptiness. It becomes an interstellar exile, a refugee tumbling through the dark. In 2017, we met our first confirmed guest, a strange cigar-shaped object named Oumuamua. It was a fleeting, ghostly encounter. 2 years later, a second visitor, 2I, Borisov, arrived looking and behaving much more like the comets we knew. They were astonishing discoveries, proof that our solar system was not an island but a coastline on a vast cosmic ocean. Yet both in their own ways followed the script. They obeyed the rules. And the primary rule, the most sacred and simple commandment for any object falling toward our star, is this: the sun is a furnace. As a frozen wanderer from the outer dark crosses the orbit of Jupiter, of Mars, of Earth, it is subjected to a relentless and ever-increasing assault. The sun's light, a torrent of photons, acts as a celestial blowtorch striking the object's surface. Its gravity squeezes and torques it. This is the moment of awakening. The ancient deep-frozen ices, water, carbon dioxide, nitrogen, methane, that have been locked in stasis for eons can no longer remain solid. They begin to sublimate, turning directly from a solid into a gas erupting from the surface in violent, glittering jets. This process, this outgassing, is what gives a comet its life. It creates the beautiful ethereal coma, the glowing atmosphere of gas and dust that surrounds the nucleus. It unfurls the magnificent tail, a banner of ionized gas and reflective dust pushed back by the solar wind, stretching for millions of kilometers across the sky. The comet, once a dead, inert rock, begins to sing a song of its own destruction, a hymn of melting ice and escaping gas. It is a glorious, predictable, and beautiful death. It gets brighter, it gets warmer, it sheds its mass. This is what comets do. It is their nature. It is the law. On a cold night in Hawaii, high atop the volcanic slopes of Haleakala, one of our planet's unblinking eyes was dutifully scanning the heavens. This was Atlas, the asteroid terrestrial impact last alert system. Its primary mission is not discovery but defense. It is a sentinel programmed to find any near-Earth object that might pose a threat to us, a silent guardian against impact. Its robotic telescopes survey the entire accessible sky every few nights, taking rapid-fire images which are then fed into powerful computers. The software's job is to play a cosmic game of spot the difference, comparing new images to old ones, looking for any tiny pinprick of light that has moved against the static backdrop of distant stars. On one such night, the system flagged a new smudge. It was faint, unassuming, and impossibly far away. At first, it was just another designation in a catalogue overflowing with them. But as observatories around the world began to track its path, a new story began to emerge from the meticulous calculations of celestial mechanics. The incoming data was fed into simulations that charted the object's trajectory backward in time, tracing its journey through our solar system. The computers drew its path, an elegant sweeping arc. But this arc was not the closed elliptical loop of a local comet forever bound to our sun's gravity. This was a hyperbola, the unmistakable signature of an unbound object, a traveller merely passing through. Its velocity was too high, its angle of approach too steep. It was not one of ours, it had come from the outside. The International Astronomical Union conferred its official designation 3I, Atlas. The 3I was a landmark, the third confirmed interstellar object in human history. A thrill rippled through the global community of astronomers. Here was a new messenger from the void. Unlike the enigmatic Oumuamua, which was already heading away when we found it 3I, Atlas was inbound. We had time, we could prepare. The world's greatest telescopes, from the deserts of Chile to the frozen peaks of Mauna Kea, began to turn their vast mirrors toward this faint speck of light. They were eager to witness its awakening, to analyze the chemical composition of its pristine alien ices. As they were vaporized by the Sunday, they were ready to read the message it carried. What they saw at first was perfectly normal. As 3I Atlas moved closer, it began to brighten just as expected. A faint coma started to form around its nucleus, a ghostly halo of outgassing material. Spectrographs were trained on it, breaking its faint reflected light into a rainbow of constituent parts, searching for the chemical fingerprints of its composition. The initial readings suggested familiar elements, the same building blocks of comets we find in our own solar system. Everything was proceeding according to the script. The law was being obeyed. Scientists were poised to document the beautiful, orderly process of a celestial body being slowly unwrapped by the sun's embrace. They were watching a predictable dance of gravity and thermodynamics, a ballet that has played out countless times across the eons. But then the readings began to shift. The data started to whisper a tale of profound impossibility. It began with the light curve, the measure of the object's brightness over time. The steady, predictable increase in its luminosity began to stutter. It fluctuated in bizarre, erratic ways that didn't align with any known model of cometary activity. It was as if the object was trying to ignite, but something was smothering the flame. Puzzled teams turned to more advanced instruments employing thermal imaging to take the object's temperature directly. This should have been the simplest, most straightforward measurement of all. As an object gets closer to a heat source, it gets hotter. It is the most basic principle of our physical world. The initial readings were already surprising, showing 3I Atlas to be far colder than its distance from the sun suggested. But astronomers accounted for this, postulating that a thick, dark, insulating crust of dust might be slowing the warming process. They waited, expecting the temperature to begin its inevitable climb as the solar radiation intensified. It never did. Instead, something happened that sent a shockwave of disbelief through every observatory watching. Something that had no right to happen. Something that violated the laws of nature as we know them. As 3I Atlas continued its inexorable plunge toward the sun, getting closer every single day, the thermal readings did not go up. They went down. The object was getting colder. It was not a subtle dip. It was a significant, sustained, and undeniable drop in temperature, measured independently by multiple instruments at multiple facilities. It was as if you were walking toward a bonfire on a winter's night, only to feel an Arctic frost creep into your bones. The data was checked. The instruments were recalibrated. The software was debugged. There was no error. The numbers were real. This visitor from another star system was flying into the teeth of a stellar furnace, and it was freezing over. The paradox was absolute. The very energy that should have been boiling its surface, ripping its ices apart and flinging them into space, was somehow being absorbed or redirected in a way that resulted in a net cooling effect. It was cosmic madness, a physical absurdity. How could this be? What mechanism could possibly account for such a phenomenon? The frantic search for an explanation began. Perhaps the object was shedding its outer layers, an incredibly dark, warm, dusty crust that was flaking away to reveal a much larger, colder and more reflective core of pristine ice beneath. This would for a time cause the average temperature reading to drop, but the scale of the cooling was too extreme, too rapid for this to be the sole explanation. It would require the object to disintegrate in a way that simply wasn't reflected in the visual observations. The coma wasn't exploding in size, it was sputtering erratically. Another more exotic theory emerged, one rooted in the strange chemistry of the deep cold. Could there be a bizarre endothermic reaction occurring on a planetary scale? An endothermic process is one that absorbs heat from its environment, making its surroundings colder. We see them in chemical cold packs here on Earth. But for a reaction to be powerful enough to overcome the immense energy input from the sun and actually lower the temperature of a kilometer-wide body would require a chemical composition unlike anything we have ever imagined. It would need to be made of materials that become fantastically unstable as they warm, kicking off a chain reaction that drinks in thermal energy at an astonishing rate. If this were true, then 3I Atlas wasn't just a comet. It was a piece of alien chemistry, a frozen chemical engine whose internal processes were utterly foreign to us. It would mean that the building blocks of other solar systems could be fundamentally different, leading to planetary bodies with properties we can't even begin to predict. This single impossible fact that an object is getting colder as it should be melting has transformed 3I Atlas from a scientific curiosity into a profound system-shattering mystery. It is a ghost in the machine of celestial mechanics, a data point that refuses to fit. It challenges our models of cometary physics, of solar system formation, of the very chemistry that might be possible in the cosmos. This isn't just a strange rock, it's a gauntlet thrown down by the universe. It tells us in the clearest possible terms that our knowledge is incomplete. It hints that out there in the countless other stellar nurseries scattered across the galaxy, nature may have run experiments that produced outcomes we have never seen, outcomes that operate by a different set of rules. As 3I Atlas continues its silent, cold journey through our home, the world's scientific community is in a desperate race against time. Every photon of light captured from it, every scrap of data, is a priceless clue, for soon its gravitational encounter will be over. It will slingshot around the sun and be flung back out into the interstellar darkness from which it came, taking its impossible secrets with it forever. The message it carries is written in a language of cold fire and impossible physics, and we are only just beginning to learn how to read it. To solve the riddle of this frozen ghost, we must now turn our attention inward to the very tools and techniques we have built to listen to the cosmos and ask a difficult question: are we even capable of understanding the answer? For millennia we believed we were an island universe. Our solar system, a collection of planets, moons and debris, was thought to be gravitationally isolated, a self-contained family orbiting a solitary star in an ocean of emptiness. The vast distances between the suns were considered uncrossable voids, deserts of cold and dark so profound that nothing could ever traverse them. We were alone, and the cosmic shoreline was impossibly far away. Then on an October day in 2017, the first visitor arrived. It was given a name as strange as its appearance, Oumuamua, a Hawaiian word meaning a messenger from afar arriving first. It was no shimmering sphere or majestic icy wanderer. Instead, it was a dark, reddish, elongated object tumbling end over end through our celestial neighborhood. It was small, perhaps no larger than a city block, and utterly devoid of the gaseous halo, the beautiful coma we expect from a long-distance traveler made of ice. It was a cosmic enigma, a shard of another star system, and as it swung around our sun, it did something impossible. It accelerated, pushing away from our star ever so slightly, propelled by a force we could not see and could not explain. There was no outgassing, no tail, yet something was giving it a gentle, persistent shove. Oumuamua offered no answers. It simply flew past a ghostly messenger that refused to speak and plunged back into the interstellar dark from which it came, leaving behind a trail of confounding questions and a shattered sense of solitude. We had been visited, and we had barely caught a glimpse. The encounter taught us a profound, humbling lesson. The cosmic ocean was not empty. There were other islands, other shores, and things did in fact cross the deep. We had simply never built the right kind of nets to catch them. Then, just 2 years later, a second stranger appeared. This one was different. Named 2I, Borisov after its amateur discoverer, it was precisely what we had expected the first visitor to be. It was a magnificent classical comet, albeit one born in another solar system. As it approached the sun, its ancient ices forged around a different star began to warm and sublimate, erupting into a vast glowing coma. Its light told us a story we could understand. Spectroscopes revealed the familiar chemical fingerprints of water and carbon, confirming that the building blocks of life-bearing worlds like our own are likely common throughout the galactic disk. Borisov was a reassurance, a sign that our models of the cosmos were not entirely wrong. It was the familiar face of a stranger, a cosmic cousin dropping in for a brief hello. Between the baffling enigma of Oumuamua and the comforting familiarity of Borisov, a new astronomical reality began to crystallize. These were not once-in-a-civilization events, they were merely the first two we were equipped to notice. Our solar system is not a secluded island. It is a port of call, a gravitational harbour on a vast interstellar shipping lane. Countless objects torn from their parent stars by ancient gravitational skirmishes are adrift in the Milky Way, a hidden population of celestial nomads. For eons, they have been drifting through our system unseen and undetected. Now, with our modern eyes, we had finally seen 2 of them. The hunt was on. The scientific community, buzzing with this new frontier, knew it was only a matter of time before a third appeared. The question was no longer times if times we would find another, but times when asterisk. And what story would it tell? Would it be another perplexing riddle like Oumuamua, or a familiar emissary like Borisov? The universe, it seemed, was preparing its next revelation. We just had to be watching when it arrived, and we times were times watching. Not with a single telescope, but with a global network, a planetary defense system with an unintended extraordinary purpose. It is called ATLAS, the Asteroid Terrestrial Impact Last Alert System, a collection of robotic telescopes stationed in Hawaii, Chile, and South Africa, working in perfect concert, their unblinking eyes scanning the entire dark sky every 24 hours. Their primary mission is a somber one: to find asteroids and comets on a collision course with Earth, to give us a final warning of impending impact. It is our planet's sentinel, a tireless digital watchman against threats from within our own solar system. But in searching for our nearest neighbours, Atlas casts an impossibly wide net. It photographs vast swathes of the cosmos, building a dynamic map of the moving sky, cataloguing millions of faint glimmers against the static backdrop of distant stars. Most are familiar points of light on predictable paths, but every so often something new appears. A flicker where there was nothing before, a single unassuming dot of light moving with intent. On a cold night in early 2022, the system flagged one such dot. It was faint, desperately faint, a mere whisper of photons collected from the darkness. To the automated software, it was simply another anomaly, an object designated A10BMLZ, requiring human verification. But as astronomers around the world were alerted and began to train their own instruments on that tiny patch of sky, a remarkable story began to unfold from that simple point of light. Night after night, they plotted its position, charting its course through the heavens. The initial calculations were routine mapping its orbit within our solar system, yet the numbers didn't fit. They didn't resolve into the gentle, closed loop of an ellipse, the shape that binds every planet, moon, and asteroid to our Sunday. The more data they collected, the more the object's trajectory sharpened into something else entirely. It was a hyperbola, a dramatic open-ended curve, the unmistakable signature of a gravitational escapee. This object was not circling our sun, it was merely passing through. It was a cosmic tourist, an unbound traveller on a one-way journey. But the trajectory was only half of the astonishing truth. The other half was its speed. Even after accounting for the sun's immense gravitational pull, the object was moving far, far too fast. Imagine throwing a stone into the air. If you throw it gently, it falls back. Throw it harder and it goes higher before returning. But if you could throw it with enough velocity, with what we call escape velocity, it would break free of Earth's gravity entirely and never come back. This object was moving with a velocity so great, it was clear it had not originated from our sun's gravitational well. It had fallen into our solar system from the interstellar, deep, carrying with it the momentum of its journey across untold light years. It was the celestial equivalent of a cannonball fired from a distant star, screaming through our cosmic backyard at over 100,000 kilometers per hour. There was no doubt. This was it, the third one. The official designation came swiftly, 3I, Atlas. The 3I standing for the third confirmed interstellar object in human history. The great net of Atlas had caught another messenger from the void. Immediately, the global astronomical community focused its collective gaze. Every great observatory, every powerful telescope capable of seeing it turned to this faint speck of light, hungry for the secrets it carried. What was it made of? What star did it call home? And which of its predecessors would it resemble, the ghost or the comet? Its path, now plotted with exquisite precision, held the first tantalizing clue. 3I, Atlas, was on a truly extraordinary trajectory, one that would take it on a death-defying plunge toward the heart of our solar system. It was destined to swing around the sun at a blistering proximity, passing far closer to our star than Mercury, the innermost planet. It would fly through the most intense region of our solar system, a crucible where temperatures soar to hundreds of degrees Celsius, where the solar wind becomes a torrential storm of charged particles, and where the light of the sun is a relentless, overwhelming blowtorch. For any object composed of ice, the very definition of a comet, this journey would be a trial by fire. A spectacular self-destructive display was all but guaranteed. We knew what times should times happen. We have seen it countless times with our own homegrown comets as they make their periodic journeys from the cold outer dark. As 3I Atlas approached this inferno, its surface should have begun to boil. Primordial ices, frozen for billions of years in the interstellar night, should have flash vaporized under the intense stellar radiation. Water, carbon monoxide, methane and ammonia should have erupted from its core, shrouding the object in a vast incandescent cloud, a brilliant coma. This expanding atmosphere, pushed back by the solar wind, should have blossomed into a magnificent tail, a shimmering banner of gas and dust, stretching for millions of kilometers across space. The object should have brightened dramatically, becoming a beacon. It was a simple, confident prediction based on everything we knew about comets. The closer it got to the sun, the more spectacular its transformation would be. We pointed our most sophisticated instruments at it, ready to witness the fireworks. We prepared the spectroscope's tools that act like cosmic prisms, slicing the faint light from the object into its constituent colors. Within that rainbow, that spectrum, we expected to find the chemical signatures of vaporizing ice. We were looking for the telltale absorption lines of water molecules, the unique spectral fingerprints of cyanogen and other volatile compounds. This was the language of comets, a language we knew how to read. We aimed our photometers, which measure an object's precise brightness over time. We expected to see its light curve steadily climb as the coma grew larger and more reflective, gathering the sun's light. The entire world of astronomy held its breath, waiting for 3I, Atlas, to awaken. It was a moment pregnant with anticipation, the opening act of a grand cosmic drama. But the drama never came. As 3I Atlas plunged deeper and deeper into the sun's searing embrace, the data that streamed back to Earth was not triumphant but deeply, profoundly strange. The spectroscopes returned a verdict of near-total silence. The expected chemical signatures, the vibrant signs of sublimating water and gas, were simply not there. There was no spectral evidence of a burgeoning atmosphere. The object's light was just that, the simple reflected light of a solid surface. It was a spectral void, an eerie absence of the very chemistry that defines a comet. the photometers told an equally unsettling story. The object was not getting brighter in the way it should have been. Its luminosity remained stubbornly constant, increasing only by the predictable amount for a bare, inert rock getting closer to a light source. There was no magnificent coma blooming into existence. There was no tail unfurling behind it. The object remained a stark, solitary point of light. It was flying through a celestial furnace that should have torn it apart, an environment that should have forced it to outgas violently, and yet it remained dormant, impassive, almost defiantly inert. It was behaving less like a comet and more like an asteroid, a dry, sterile chunk of rock and metal. But that conclusion created an even more baffling paradox. If it were just a rock, how could it have survived its journey? Rocky objects are believed to be far more brittle, more susceptible to being shattered by tidal forces and thermal stress. An icy body, a cosmic snowball, has more tensile strength. It's better equipped to hold itself together during a close stellar pass. So here was the conundrum, the central mystery of 3I, Atlas. It was on the orbit of a comet, plunging toward the sun like a comet. It times should times have been a comet. But it refused to act like one. It was a traveler from another star facing imminent incineration, and it was doing nothing. This wasn't the enigmatic acceleration of Oumuamua, nor the familiar performance of Borisov. This was a new kind of impossible. An object that was withstanding conditions that should have vaporized it. An object that was breaking all the rules we thought we understood. The great messenger from afar had arrived, and its first message was silence. A silence so profound it was more deafening than any explosion. The mission to understand 3I, Atlas, had just begun, and already it was forcing us to question the very nature of the objects that wander the great dark ocean between the stars. What is this thing made of? How is it surviving the sun's unrelenting fire? And as it endures this crucible, a deeper, more chilling mystery is about to unfold. A behavior so counterintuitive, so contrary to the laws of thermodynamics, it will challenge everything we think we know. The object that should be melting, that should be boiling away into nothing, is somehow impossibly getting colder. And so the moment of judgment arrived. For 3I, Atlas the Sun was no longer a distant beacon, a gravitational guidepost in the void. It was now a physical presence, an all-consuming furnace that filled its sky. From our vantage point 150 million kilometers away, we could only watch and wait. The world's observatories, a global network of glass and steel, swiveled in unison, their gaze fixed on a single insignificant point of light, executing a thread-the-needle maneuver through the most hostile environment in the solar system. This was the trial by fire, the ultimate test of its enigmatic nature, a crucible forged from the very star it was now challenging. Every model we possessed, every simulation run on our most powerful supercomputers, predicted a dramatic, perhaps even a terminal transformation. At this proximity, the sun's radiation becomes a relentless physical force, a celestial blowtorch powerful enough to peel the surface from a world and ignite its frozen heart. We were expecting a spectacle. We were prepared for a disintegration. What we received instead was the beginning of an even deeper, more profound enigma. The first stream of data to pour in from our planet's collective retina was perhaps the most fundamental, its light curve. This is the object's heartbeat, a simple graph plotting brightness over time. For any inbound comet, this curve is a predictable crescendo. As it nears the sun, solar energy excites the ices buried within its nucleus, causing them to sublimate directly into gas. This expanding cloud, the coma, swells to enormous size, sometimes larger than Jupiter, and catches vastly more sunlight than the tiny nucleus ever could. More gas means more dust is liberated, unfurling into a magnificent tail that acts like a colossal cosmic mirror. The light curve, therefore, should have been a steep, dramatic ascent, a spike of brilliance announcing its fiery awakening. For weeks, astronomers watched their screens anticipating this very surge. And at first, 3I, Atlas, seemed to oblige its brightness, ticking upward as it fell deeper into the sun's gravitational well. But the climb was sluggish. It was lethargic, lacking the explosive enthusiasm of a truly active comet. It was the gentle swell of a wave, not the erupting volcano we had been promised. Then, as it rounded the sun, at the very moment its brightness should have peaked in a blaze of glory, the unthinkable happened. The light curve flattened. It simply stopped rising, hanging in the sky with a strange, defiant constancy. Teams in Chile traded frantic messages with their counterparts in Hawaii. Was it an instrument calibration error? A flaw in the atmospheric correction algorithms? Multiple independent observatories using different instruments and different methods all returned the same impossible result. The object was refusing to get brighter. It was as if it had a thermostat and had decided it was quite warm enough. And then the data took a turn that sent a chill through control rooms around the world. As it began its journey away from the sun, still blisteringly close, its light curve began to dip. It wasn't just failing to brighten, it was actively getting dimmer. This was a flagrant violation of cometary physics. It was like throwing a log on a fire and watching the flames shrink. The very energy that should have been feeding its brilliance seemed to be suppressed. The heartbeat we were monitoring wasn't just weak, it was becoming fainter precisely when it should have been pounding with celestial fury. This perplexing signal was soon joined by a stark visual reality. The great observatories, their adaptive optics piercing the glare of our own atmosphere, delivered images of breathtaking clarity. We had all seen the simulations, the glorious artists' impressions of what 3I, Atlas, should look like at perihelion, a radiant star-like head wrapped in a glowing green shroud of diatomic carbon with twin tails of ionized gas, reflective dust stretching for millions of kilometers across. The black. We were braced for a spectacle to rival the great comets of history. The first processed images that appeared on monitors were met not with gasps of awe, but with stunned, confused silence. There was no grand tail. There was no brilliant coma. Where there should have been a celestial phoenix, there was only a point, a sharp, lonely, stubbornly stellar point of light. Under the highest magnifications, we could resolve a vanishingly faint, tenuous fuzz surrounding it, a pathetic ghost of the coma it was supposed to have. It was thousands of times less active, less productive than our models had insisted it must be. It was as if the object was wrapped in some kind of invisible shield, deflecting the worst of the solar onslaught. The sun was screaming at it, and 3I, Atlas, was refusing to answer back. The sheer volume of water ice that should have been vaporizing every second enough to fill an Olympic swimming pool was simply missing in action. Where had it all gone? Or the more frightening question, was it ever there to begin with? This led directly to the third pillar of our investigation, its motion. We can track the position of objects in space with astonishing precision, predicting their paths years in advance based on the elegant, unwavering laws of gravity. But comets are messy. They are not perfect gravitational dance partners. As their ices turn to gas, they erupt from the surface in powerful jets acting like tiny, unpredictable rocket thrusters. These forces, known as non-gravitational accelerations, gently but measurably push the comet off its purely gravity-defined course. For an object as close to the Sun as 3I, Atlas now was these jets should have been firing with incredible power, making its trajectory wobble and drift. It's a key signature of outgassing the dynamic proof that the object is alive and active, so we watched its path. The global network of radar and optical telescopes measured its position with a precision down to meters. Every hour its location was plotted against the flawless arc predicted by gravity alone. And every hour the result was the same. It was a perfect match. There was no deviation, no wobble, no drift, no push, nothing. The data was so clean, so terrifyingly perfect, it could have been a textbook example of orbital mechanics. 3I, Atlas, was moving like a dead rock. It was a gravitational purist, ignoring the tempest of solar radiation it was flying through, behaving as if the sun were nothing more than a simple point of mass. The lack of a tail was visual evidence. This was the cold, hard mathematical proof. The engines were off. The rocket thrusters were silent. The object was against all logic inert. It was an anchor against the solar storm, a ghost in the machine of the solar system obeying gravity and nothing else. With our expectations so thoroughly shattered, we turned to our last and best hope for an answer: spectroscopy. By passing the faint reflected light from 3I, Atlas, through a prism, we could spread it into its constituent colours, a rainbow barcode of its chemical composition. In this spectrum, we hoped to find the object's soul. We would search for the characteristic absorption lines of water ice, the emission bands of cyanogen and carbon, the telltale fingerprints of the molecules that make up a comet. This surely would be the Rosetta Stone. If it wasn't made of conventional ices, the spectrum would tell us what it was made of. Perhaps it was a bizarre dehydrated remnant of another star system composed of exotic high-temperature minerals that simply didn't vaporize. The faintness of the object made the task agonizingly difficult. For nights on end, the world's largest telescopes had to stare unblinking at that single point, collecting photons one by one like filling a bucket in a drizzle. The science teams weighted their careers and reputations hanging on the result. When they had finally gathered enough light to produce a reliable spectrum, the sense of anticipation was electric. The data was processed, the noise was filtered out, and the final graph was rendered. It was a blank page. The spectrum was an almost perfectly featureless continuous slope. It was a near-perfect reflection of the sun's own light, with no significant identifiable absorption or emission lines to give us a foothold. There was no strong signature for water ice, no hint of carbon dioxide or methane, no trace of the organic molecules we expect to see in cometary comas. There was only a gentle reddish tinge across the spectrum, indicating a surface that was generic, unremarkable. It was the kind of spectrum you might get from a mundane carbonaceous asteroid from our own solar system's outer belt. But asteroids don't come from interstellar space on wild hyperbolic trajectories, and a simple dead asteroid should have been heated to a glow at this distance, its thermal emissions painting a clear picture in the infrared. Yet infrared telescopes also saw less heat than expected. The object was confounding our most sophisticated diagnostic tool by being utterly maddeningly plain. It was offering us no clues. It was a master of cosmic misdirection wearing a disguise of absolute neutrality. It was actively hiding its identity from us, reflecting our own star's light back at us as if in mockery. We were left adrift in a sea of contradictions. We had an object that was traveling like a comet from another star, but which steadfastly refused to act like one. Its light curve suggested it was shutting down under the sun's intense glare. Its physical appearance showed a shocking lack of the coma and tail that should have been its defining features. Its trajectory was that of a dead, passive rock, unswayed by the outgassing forces that should have been tearing it apart. And its chemical fingerprint was a meaningless, featureless void. Every single piece of evidence we gathered only deepened the mystery. Each observation, instead of providing an answer, simply added another, more perplexing question to the pile. The very foundation of our planetary science, the clear and trusted distinction between a rocky, inert asteroid and a volatile, icy comet, was crumbling before our eyes. This visitor was neither. It was a third thing, a category of object for which we had no name and no theory. And through it all, the central paradoxical absurdity remained. An object plunging through a crucible of pure starfire, subjected to temperatures that can melt lead, was not only failing to vaporize, but was, according to some of our thermal models, presenting an effective temperature that was, inexplicably, stable, even perhaps becoming colder than it had any right to be. The heat being poured onto its surface by the sun seemed to be going somewhere, but it wasn't radiating back out as expected, nor was it driving the spectacular outgassing we were so sure we would see. The laws of thermodynamics themselves seemed to be under scrutiny. The conservation of energy demanded that the immense solar radiation had to go somewhere, but where we were no longer just observing a celestial body, we were confronting an impossibility. We had come seeking a comet and had found a paradox wrapped in a mystery coasting silently through the heart of our solar system, leaving behind nothing but a trail of broken theories and unanswered questions. The moment of truth, the trial by fire, had passed. For weeks, we held our collective breath as 3I Atlas plunged into the searing heart of the inner solar system, a fleeting visitor from the interstellar dark making its suicidal charge toward our star. Every model, every calculation based on a century of observing comets and asteroids screamed a single inevitable verdict: annihilation. It should have cracked, shattered, and then sublimated into a glorious incandescent cloud of vapor and dust, a transient firework against the velvet black. It was supposed to die a spectacular, predictable death, under the relentless gaze of the sun, the ultimate celestial blowtorch. And yet, as the object rounded the sun and began its long climb back out of the gravitational well, a profound and unnerving silence descended upon the world's observatories. There was no grand explosion. There was no blossoming tale of liberated gas and debris visible to every backyard telescope 3i, Atlas, had endured. It had survived its fiery pilgrimage, a feat that in itself was deeply unsettling. The initial data trickling back confirmed its structural integrity, a defiant act of cosmic resilience that left astronomers baffled. But this initial mystery, the simple fact of its survival, was merely the quiet prelude to a revelation so profound, so utterly contrary to the known laws of physics that it would threaten to rewrite our understanding of matter itself. The real story wasn't that 3i, Atlas, had survived the heat. The story was what the heat had done to it, or rather what it hadn't. To understand the impossible discovery that followed, you have to peer into a universe invisible to our eyes, a world painted not in light and shadow, but in heat and cold. Our primary tools for this exploration were not the great optical telescopes that see invisible light, but their sophisticated cousins, the infrared observatories. Titans of technology like the now retired Spitzer Space Telescope and its powerful successor, the James Webb Space Telescope, are designed to detect thermal radiation, the faint glow of heat emitted by every object in the cosmos. Think of them as the ultimate cosmic thermometers, capable of taking the temperature of a pebble from millions of miles away. They don't see an object, they see its thermal signature, its heat ghost cast across the void. When we pointed these instruments at 3i, Atlas, during its approach the readings were already unusual, but within a bizarre kind of reason. Its sun-facing side was warming just as expected, though perhaps not as quickly as our models predicted for a dark, rocky body. We chalked it up to an unusually high albedo, a reflective surface that was bouncing more solar energy back into space than it absorbed. We theorized a surface of exotic mirror-like ices, or perhaps a metallic sheen, unlike any asteroid we had ever catalogued. It was an interesting but perhaps solvable puzzle. The real test, the data everyone was waiting for, would come after perihelion, in the moments and days after it had soaked up the maximum possible dose of solar radiation. An object that close to the sun behaves like a blacksmith's anvil pulled from the forge. It glows. It radiates heat ferociously back into the cold vacuum of space. According to the fundamental laws of thermodynamics, 3i, Atlas, should have emerged from its solar encounter, blazing in the infrared spectrum, its surface temperature soaring to hundreds of degrees Celsius. It should have been a beacon of stored thermal energy, slowly, predictably, and gracefully cooling as it coasted back toward the cold outer darkness from whence it came. Every single object we have ever observed in our solar system, from the smallest meteoroid to the planet Mercury, obeys this simple, immutable law of physics. You absorb energy, you heat up. You move away from the energy source, you cool down. The first post-perihelion temperature readings from the Atacama Large Millimeter Array in Chile were so strange the team leader initially classified them as instrument error. The data was quarantined, the systems were recalibrated, and the observations were run again. The results came back the same. Then confirmation arrived from space-based platforms free from any atmospheric distortion. The numbers they sent back to Earth didn't just challenge our expectations, they staged a rebellion against them. 3i, Atlas was not glowing incandescently in the infrared. In fact, it was shockingly, unnervingly dim. The temperature of its sun-baked surface was not the expected 400 or 500 degrees Kelvin. It was barely above 150 Kelvin. That's a staggering negative 123 degrees Celsius, or negative 190 degrees Fahrenheit. It was colder than the surface of Jupiter's moon Europa, a world that lives its entire life in the frigid twilight, almost 800 million kilometers from the sun. This object, having just skimmed a star, was registering temperatures you'd expect to find in the Kuiper Belt, out beyond the orbit of Neptune. It was an impossible reading a piece of data that screamed absurdity. It was like pulling a red-hot iron from a fire and discovering it was now coated in frost. The initial shockwave through the astronomical community was one of frantic problem-solving. Every conventional explanation was thrown at the paradox. Could the object be spinning at an unbelievable rate, thousands of revolutions per second, distributing the heat so efficiently that no single point ever got truly hot? The physics of such a rotation would have torn any known material apart from the sheer centrifugal force. Could it be a perfect mirror, an object with an albedo of nearly 1 reflecting virtually all solar energy? While theoretically possible, such a perfect natural surface has never been observed, and it wouldn't explain what happened next. Because the true reality-bending discovery was yet to come. It wasn't just that 3I, Atlas, was anomalously cold after its encounter. It was that as it continued to move away from the sun, it was getting even colder, and at a rate that defied all logic. Day by day, as the distance between it and the sun grew, its temperature didn't just decrease along a predictable cooling curve. It plummeted. The temperature drop was too fast, too steep, too aggressive. It wasn't behaving like a passive object releasing stored heat. It was behaving as if it had an active refrigeration system. It was as if some internal process, some unknown physical mechanism was actively pumping heat out of its surface, bleeding thermal energy into space at a rate that our physics could not begin to explain. This is the central, terrifying paradox of 3I, Atlas. It is the observation that transformed it from a mere curiosity into a profound crisis for astrophysics. An object cannot get colder faster than the laws of thermodynamics permit. It cannot shed heat it hasn't absorbed. The energy balance must be maintained. The sun pours a known quantity of energy onto its surface. That energy has to go somewhere. It can be reflected, or it can be absorbed and then re-radiated as heat. There is no third option in our physics books. Yet 3I, Atlas, presented us with a third option, a cosmic magic trick playing out on an interplanetary stage. It was absorbing a torrent of solar energy, yet its surface remained inexplicably frigid. It was a thermal vampire drinking in the light and heat of our star and giving back only impossible cold. Debate erupted in university halls and on encrypted scientific forums. The intellectual battle lines were drawn. On one side were the conservatives desperately trying to find a natural if exotic explanation. They proposed bizarre material compositions like a porous aerogel-like structure of unknown interstellar matter. In this model, the sun's heat would penetrate deep into the object's core, instead of heating the surface, a process called thermal insulation. The heat would become trapped, leaving the surface layer deceptively cold. This was a clever and elegant theory, but it had a fatal flaw. It couldn't account for the rapid active cooling observed post-perihelion. An insulated object would cool down slower times than a normal one, not faster. The trapped heat would eventually have to leak out, keeping the surface warmer for longer. We were seeing the exact opposite. Others hypothesized some form of endothermic reaction. Perhaps they argued the sun's intense radiation was triggering a chemical or physical change on the object's surface, a continuous reaction that, like a chemical cold pack, actively absorbs heat from its surroundings. This was a more radical idea, as it would require a substance with properties we've never encountered. What kind of material could sustain such a powerful heat-absorbing reaction for weeks on end under the full blast of the sun? What could possibly be its chemical makeup? No known molecule or element could account for the colossal amount of energy that was simply vanishing from the equation. The energy budget was so wildly out of balance that it was as if a law of nature, the conservation of energy, had been locally suspended in the space around this one object. A special consortium was formed, a thermophysics anomalies task force pooling observation time from every major infrared and radio telescope on the planet. They mapped the object's thermal signature with excruciating precision, hoping to find a hotspot, a plume of vented gas, anything that might act as a thermal exhaust port, and explain where the energy was going. They found nothing. The cold was uniform, a perfect cryogenic shield wrapped around the entire body. The data was irrefutable, cross-checked by teams across the globe who were terrified of staking their reputations on such an outlandish claim. But every new observation only deepened the mystery, confirming the impossible reality. The object that should have melted was against all logic, freezing itself in the face of the sun. This discovery was the story's midpoint, the dramatic turn that elevated 3I, Atlas, from an astronomical puzzle into a philosophical earthquake. We were no longer just asking what it was made of. We were forced to confront a far more disturbing set of questions. Is our understanding of thermodynamics incomplete? Is there a state of matter forged in the crushing voids between stars that behaves in ways we can't predict? The phenomenon was so alien, so profoundly non-natural in its behavior, that for the first time a hushed and controversial word began to be whispered in the corridors of science, a word most researchers spend their entire careers avoiding artificial. The idea was scientific heresy, the stuff of late-night talk shows and pulp fiction novels, but the data was pushing us into these uncomfortable corners. An object that actively manages its thermal signature, that maintains a cold exterior while absorbing immense energy, sounds less like a rock and more like a machine with a purpose. Was this some form of thermal regulation, a sophisticated heat sink, or a radiator of unimaginable efficiency designed to protect something within? Could this object be a vessel, a probe, its cold skin, a form of stealth hiding its true nature from thermal detection? These were not questions astronomers were comfortable asking. The implications were too vast, too destabilizing to our view of the universe and our place in it. The getting colder phenomenon became a stark dividing line. It was the point where all conventional models failed, leaving a vacuum that could only be filled by radical and perhaps terrifying new ideas. We had observed an object that appeared to hold a mastery over energy that bordered on the magical. It had faced the full, unbridled power of a star and responded not with disintegration, but with a quiet, defiant, and impossible cold. It was a cryptographic puzzle written in the language of heat, and we, for all our accumulated knowledge, did not possess the key to decipher it. The object was no longer just a visitor, it was a statement, and as it continued its silent journey back into the depths, it left us with a chilling realization: we had just been shown something that should not exist, and the universe we thought we knew would never look quite the same again. The search for its true nature had just begun, and the next steps would take us even further from the comfortable shores of known science and into the uncharted, turbulent waters of pure speculation. The data stream solidified into a new, terrifying constant. The initial shockwave that had ripped through the astronomical community, a mixture of disbelief and exhilarating discovery, was now settling into something far more unnerving, a protracted, grinding siege against the laws of physics themselves. In observatories from Mauna Kea to the Atacama, the hushed reverence of discovery had been replaced by the frantic energy of a crisis. Whiteboards, once pristine with orbital mechanics, were now chaotic palimpsests of scrawled equations and abandoned theories, each one a testament to a failed attempt to domesticate the anomaly. 3I, Atlas, was no longer just an interstellar visitor. It was an intellectual insurgency, a cold, silent rebellion against everything we thought we knew about the universe. And as it continued its inexorable fall toward the sun, getting colder with every passing million kilometers, the question was no longer times what times it was, but how it could possibly times be asterisk. The first line of defense against the impossible is always to expand the definition of the possible. If an object refuses to melt under a cosmic blowtorch, the most logical starting point is to assume it's made of something that cannot be melted. This was the dawn of the exotic materials hypothesis, a period of frantic theoretical metallurgy on a cosmological scale. Physicists and materials scientists, who usually concern themselves with designing turbine blades or semiconductor substrates, were pulled into the astronomical fray. Their task was to computationally invent a substance, any substance that could withstand the thermal hell awaiting 3I, Atlas. They began with known super-refractory materials, the champions of our terrestrial high-temperature engineering. Compounds like tantalum hafnium carbide, which boasts the highest known melting point at nearly 4,000 degrees Celsius, became the baseline. Simulations were spun up on supercomputers across the globe, each one a digital crucible. In these virtual realities, titanic slabs of hypothetical matter were bombarded with a simulated solar wind of blistering intensity. Scientists modeled materials with molecular bonds of ferocious strength atomic lattices so perfectly interlocked They vibrated with a quantum hum, but refused to break. They envisioned crystalline structures forged in the heart of a neutron star, or perhaps in the unique high-pressure furnace of a core-collapse supernova of a metal-rich first-generation star. These were not mere asteroids. They were imagined as cosmic anvils, mountain-sized artifacts of physics, operating at its most extreme. For a brief, hopeful period, this seemed like a plausible path. It suggested that the universe simply had a deeper toolbox than we had previously imagined. 3i, Atlas, wasn't breaking the rules. It was just playing with a set we hadn't been given access to yet. But the universe, it seems, rarely offers such simple solutions. The fatal blow to the exotic materials hypothesis came not from a supercomputer, but from the unblinking eyes of our most powerful telescopes. While a superrefractory substance would indeed explain the object's structural integrity, it would also have a distinct chemical fingerprint. It would absorb and reflect sunlight in a very particular way. Every element, every compound sings its own song written in light, a unique spectral signature that we have become exquisitely skilled at reading. And when the spectrographs from the James Webb Space Telescope delivered their verdict, the scientific community felt a collective sinking feeling. There were no strange, spiky emission lines indicating undiscovered ultra-dense metals. There were no absorption bands hinting at exotic carbon allotropes. The light bouncing off 3i, Atlas, told a story that was almost insultingly mundane. It looked dirty. The signature was overwhelmingly that of amorphous carbon and silicates interspersed with complex organic molecules like tholins. It was the spectral profile of a common garden-variety carbonaceous asteroid, the kind of rubble that fills our own asteroid belt. The object that was defying a star was for all intents and purposes composed of the same stuff as a lump of cosmic coal. The revelation was staggering. It was like discovering a firefighter walking through an inferno completely unharmed, only to find he is wearing simple cotton pajamas. The material itself could not be the answer, and this still left the greater, more profound mystery utterly untouched. A heat-resistant shield explains survival. It does nothing, absolutely nothing, to explain the chilling, the active temperature drop that was now accelerating as the object drew closer to the sundae. It was one thing to not melt. It was another thing entirely to behave like a cosmic cryo-engine. The first theory had not just failed, it had failed so spectacularly that it made the problem even more profound. With materials ruled out, the focus had to shift. If the times substance times wasn't special, perhaps its times structure times was. The second great wave of speculation began the internal architecture hypothesis. The idea was that 3i, Atlas, might be a natural yet highly unconventional thermal machine. Perhaps it wasn't a solid monolithic body, but a celestial thermos of unimaginable efficiency. Theorists posited a highly porous interior, a fractal-like labyrinth of voids and chambers. This internal structure could act as a near-perfect insulator, with vast pockets of hard vacuum separating thin, rocky membranes. Heat struggling to propagate through this complex honeycomb would be trapped and slowed, unable to penetrate the object's core. Some models went further, suggesting a layered, onion-like composition. Imagine a series of concentric shells, each separated by a vacuum gap, not unlike the construction of a Dewar flask you might use for coffee. In this scenario, the outer layer might heat up, but it would radiate that heat away into space before it could conduct it to the next layer down. This was a more sophisticated, more elegant solution. It didn't require inventing new physics, only imagining nature as a far more clever engineer than we had ever given it credit for. Could such a structure form naturally? It was a stretch. Perhaps during a chaotic planetary formation, a protoplanet was shattered and rapidly reaccreted, trapping vast voids inside. Or maybe it was the remnant of a giant frozen comet whose volatile ices had sublimated away from the inside out, leaving behind a delicate sponge-like skeleton of carbon and rock. The models were beautiful, intricate, and for a while they held a certain seductive power. They painted a picture of 3i Atlas as a marvel of natural engineering, a silent, passive object whose trick was simply its impossibly clever geometry. It was a comforting thought, an answer that kept the phenomenon squarely within the realm of known science. Yet, like the theory before it, the structural hypothesis soon began to crumble under the relentless assault of the data. The problem was the surface. Insulation protects the interior of an object, but it does nothing to cool the exterior. The outermost layer of this hypothetical cosmic thermos, the part directly exposed to the sun, should still be absorbing radiation. It should be glowing, heating up to hundreds if not thousands of degrees. But the infrared telescopes were unequivocal. The surface of 3I, Atlas, the very skin of the object, was the part that was getting colder. The insulation model predicted a hot surface and a cold core. We were observing a cold surface that was actively becoming colder. This led to an even more glaring contradiction with fundamental physics. The first law of thermodynamics, the sacred principle of conservation of energy, states that energy cannot be created or destroyed. The sunlight striking 3I, Atlas, is a colossal amount of energy. If the surface isn't heating up and the energy isn't being conducted to the interior, then where is it going? It has to go somewhere. The object isn't glowing in some other unseen wavelength. It isn't sprouting a cometary tail of vaporized material that could carry the energy away. The energy being pumped into it by the sun was simply disappearing. It was being absorbed by the dark carbonaceous surface and then vanishing from the universe's ledger. The structural hypothesis had not only failed to explain the cooling, it had created a new, even more profound paradox, a black hole of energy in direct violation of the most basic laws of reality. The frustration in research circles was palpable. It felt like the universe was not just presenting a puzzle but actively cheating. With the two most plausible natural explanations in ruins, the scientific community found itself backed into a terrifying intellectual corner. When passive solutions fail, you are forced to consider active ones. This marked the beginning of the third and most radical phase of speculation, the search for an unknown cooling mechanism. This was a paradigm shift. Scientists were no longer asking how the object was, times surviving, times the heat, but how it was actively times, pumping, times it away. They were forced to contemplate the possibility that 3I, Atlas, was not a passive rock, but a dynamic, active system. The idea felt like a trespass into science fiction, but the data left no other choice. One of the first proposals centered on a massive, sustained endothermic reaction. In chemistry, some reactions don't release heat. They absorb it from their environment. A simple chemical cold pack is a common example. Could 3I Atlas be a planetary-scale cold pack? Theorists dove into the esoteric fringes of cryochemistry, searching for a reaction that could hypothetically absorb such a staggering amount of solar energy. Perhaps some unique combination of elements forged in its home star system and stable only at near absolute zero was now undergoing a massive phase transition as it was gently warmed. This process, like ice melting into water, absorbs energy. But to account for the observed cooling, the scale of this reaction would have to be biblical. It would require an entire body composed of a substance that could continuously undergo this change, a planetary engine of phase transition. But once again, the spectrographs remained stubbornly silent. A chemical reaction on this scale, even an endothermic one, would produce byproducts. There would be exhaust, to change in the surface composition times something, times to indicate a process was underway. 3I Atlas showed nothing. It was chemically spectrally inert, a silent, featureless rock. Another, even more exotic idea was a form of solid-state radiative cooling. Some advanced materials can be engineered to radiate heat away in specific infrared windows so efficiently that they can cool down even under direct sunlight. It's a technology we are only just beginning to develop for terrestrial applications. Could 3I Atlas be a natural manifestation of this principle on a cosmic scale? Perhaps its surface was a naturally occurring metamaterial, a microscopic repeating geometric structure that funneled thermal energy into a narrow, transparent band of the infrared spectrum, beaming it out into space with perfect laser-like efficiency. The physics was sound in theory, but the level of structural perfection required across a body tens of kilometers in diameter beggared belief. To form by chance would be a statistical impossibility so profound it would be tantamount to a miracle, and it still felt incomplete. It explained how heat could be shared efficiently, but the sheer rate of cooling, the aggressive chilling as the solar input times increased, time still felt like it required an active, energy-consuming process. Every door that science tried to open led to a brick wall. The object wasn't made of anything special. Its structure couldn't explain the data. An active chemical process would leave evidence, but there was none. An advanced physical process seemed too perfect to be natural. The problem-solving sessions grew longer, more heated. Tempers frayed. For the first time in generations, we were facing an object in our own solar system that was utterly incomprehensible, a phenomenon for which we had no language, no framework. This growing desperation began to fuel whispers, conversations held in hushed tones at the back of conference halls or over encrypted messaging channels away from the official recorded discourse. The whispers all centered on a single taboo possibility. What if the assumption that 3I, Atlas, was a natural object was the primary error? The thought was anathema to the scientific method, which rightly defaults to natural explanations. To propose an alternative was to risk professional ridicule, to be branded a crank. Yet the logic, however unsettling, was becoming difficult to escape. When you have exhausted all possible natural explanations, the unnatural one, however improbable, remains. The object's behavior was not like a rock or a comet. It was behaving like a machine with a purpose, a machine that was actively managing its own internal temperature with an unknown technology. The term technosignature began to appear on the fringe forums, where beleaguered astrophysicists went to vent their frustrations anonymously. The idea of a non-natural origin solved all the paradoxes at once. The superrefractory problem. Its skin isn't a natural material, it's an engineered hull. The energy paradox. The energy isn't vanishing, it's being collected, stored, or used to power an internal cryo engine whose waste heat is being directed away in a method we cannot detect. The stubborn resistance to categorization. It's not a comet or an asteroid because it was never intended to be one. It is an artifact. This hypothesis was not embraced. It was a ghost that had begun to haunt the mainstream, a thought that could no longer be entirely suppressed because its explanatory power was becoming terrifyingly potent. No one wanted to be the first to say it in a peer-reviewed paper, but no one could deny that their own models were now pushing them toward the same incredible conclusion. The frustration within the community was no longer just about a failure to solve a puzzle, it was about the slow, dawning horror that the puzzle itself might not have originated from the universe we thought we knew. And so we found ourselves at a profound and deeply uncomfortable impasse. Trapped between a set of natural explanations that were demonstrably false and a single unnatural explanation that was scientifically untestable and philosophically terrifying. 3I, Atlas, was no longer just an object to be studied. It had become a mirror forcing us to confront the limits of our knowledge and the scale of our cosmic isolation. As it fell silently through the void, its impossible chill radiating into space, it prepared for its closest approach to our star. And we, the bewildered onlookers, could only watch and wait, knowing that all our theories had failed and that the object that shouldn't exist was about to face its greatest trial by fire. The answers, whatever they were, lay ahead in the inferno of perihelion, and so we were left with an impossibility. A cosmic refugee, born in the frigid dark between the stars, was now staring down the furnace of our sun, and with every passing moment it was growing colder. The closer it flew to the fire, the more ice it seemed to make. Every law of thermodynamics, the foundational logic of our universe, screamed that this could not be. Heat flows from hot to cold, always. An object bathed in stellar radiation must warm up. It must melt. Yet the data streams from our telescopes were relentless, unflinching in their contradiction of known physics. 3I, Atlas, was not just an anomaly, it was a rebellion. A quiet, frozen defiance that threatened to shatter our understanding of how energy and matter behave on the grandest of stages. For months, the world's greatest minds threw everything they had at the problem. Exotic models of sublimation magnetic shielding, bizarre albedo effects. Each one was painstakingly constructed, and each one crumbled to dust against the hard, cold reality of the observations. The jets didn't match. The cooling curve made no sense. The very existence of this object here and now was a paradox that had brought the astronomical community to a standstill. We had followed the clues to the edge of reason itself and found ourselves staring into an abyss of the unknown. It was in that intellectual darkness, in that moment of collective failure, that the first glimmer of a truly radical idea began to take shape. It didn't come from a grand observatory or a billion-dollar space mission, but from a small team of planetary geophysicists at a university in Kyoto. They weren't even studying comets or interstellar objects. Their work was focused on the crushing, unimaginable pressures deep within the cores of gas giants like Jupiter and Saturn. They were exploring a strange and violent realm of physics, where the very definition of solids, liquids, and gases breaks down a world of metallic hydrogen and superionic water states of matter so alien they can only be sustained under the weight of entire worlds. They were looking at computer simulations of how these exotic materials behave when subjected to sudden changes in temperature or pressure. And one afternoon, staring at a screen of complex thermodynamic equations, a junior researcher noticed something. A peculiar phase transition, a theoretical curiosity long dismissed as unlikely, showed a bizarre energy exchange. Under certain specific conditions of immense pressure, when a precise amount of energy was introduced, this exotic form of super-dense ice didn't just absorb the heat. It initiated a catastrophic runaway endothermic reaction. It became a thermal vampire, violently sucking energy from its surroundings to fuel its own structural transformation. The result in the simulation was a localized, instantaneous, and dramatic drop in temperature. Heat was not being reflected, it was being consumed. Suddenly, a wild, electrifying thought connected two disparate worlds, the crushing heart of a gas giant and a lone wanderer from deep space. What if 3I, Atlas, wasn't a simple snowball of ice and dust? What if it wasn't a world at all, but an engine, a crystalline machine forged in pressures we can barely comprehend and governed by a form of physics we had only ever glimpsed in theory? This new model began not on the surface but with the object's skin. We had assumed its crust was a simple insulating layer, but the Kyoto model proposed something far more intricate. This was no passive shell. It was an active, engineered surface, a kind of cosmic metamaterial. Imagine a structure composed not of simple water ice, but of a highly organized lattice of clathrate hydrates. These are crystalline cages of water molecules that trap other gases, methane, nitrogen, carbon monoxide inside. On Earth, we find them in the crushing blackness of our deepest oceans. But in the interstellar medium, under eons of cosmic ray bombardment and unimaginable cold, this team proposed something new could form. A hyperclathrate structure, layered and complex, possessing a property known as anisotropic thermal conductivity. Think of it not as insulation like a blanket, but as a network of thermal conduits like fiber optic cables for heat. This shell doesn't block the sun's energy. It catches it, channels it, and focuses it inward. The outer few millimeters of the surface might indeed heat up, explaining the initial faint readings of a normal cometary body. But this is a deception, a thermal sleight of hand, because just beneath that vanishingly thin veneer, the hyperclathrate lattice acts as a one-way heat valve. It efficiently conducts thermal energy away from the surface, plunging it down into the heart of the object while being almost completely incapable of conducting it back out. The surface is therefore constantly having its heat stolen from within, drained away into the mysterious core, faster than the sun can replenish it. You are watching the scientific equivalent of a magic trick. The sun's energy isn't disappearing. It's being drawn backstage, pulled into the depths, to power an incredible performance. And it is in those depths, in the crushing center of 3I Atlas, that the true secret lies. Here, the model departed from all known celestial mechanics. The core of this object the team proposed is not merely cold and dense. It exists in a state of extreme metastable equilibrium, a substance they named amorphous ferroelectric ice. This is not the ice you know. It is not crystalline. It is a chaotic jumble of water molecules, but one compressed under such colossal pressure that the electron shells of the atoms themselves have been distorted. The molecules are packed so tightly that their natural polarity, the positive and negative ends, are forced into a strained high-energy alignment like a trillion microscopic springs all coiled and locked in place. The entire core exists on a knife's edge of stability, a repository of immense potential energy held in check only by the staggering pressure and the absolute cold. It is a gravitational bomb waiting for a fuse. And that fuse is the heat being piped down from the surface. As the focused thermal energy from the hyperclathrate crust reaches this superpressurized core, it provides the critical activation energy. It unlocks the first few molecular springs from their strained alignment, and what follows is a chain reaction that spreads through the core with the violence of a detonation. The amorphous ferroelectric ice begins to collapse, not into a liquid, but into a more stable, lower-energy crystalline form. This is the process the simulations had hinted at: exothermic phase inversion. For this transition to occur, for the molecules to break their high-energy bonds and resettle into a comfortable lattice, they require a colossal input of energy. The process is profoundly, violently endothermic. The core becomes a cosmic refrigerator, an insatiable heat sink that begins to pull thermal energy from the surrounding mantle with unbelievable efficiency. This creates a powerful thermal gradient, a cascade of cooling that races from the core outwards through the body of the object until it reaches the inner side of the crust. The crust, that one-way thermal valve, now has its heat being drained from both sides. From the outside, the sun is warming it. From the inside, the phase-changing core is freezing it, and the internal process is winning, overwhelmingly. The surface of 3I, Atlas, is getting colder for the same reason the outside of a glass of ice water gets cold. A phase change is happening within, consuming thermal energy at a rate that defies our sun's best efforts. This single, elegant and revolutionary concept suddenly made all the disparate, confusing pieces of the puzzle snap into place with breathtaking clarity. Those mysterious jets, the plumes that contained so little water vapor and were far too energetic for simple sublimation, they were never about melting. They were exhaust ports. The phase transition in the core from a high-density amorphous state to a lower-density crystalline state would cause a dramatic increase in volume. The core is literally expanding, creating fractures and vents that blast superpressurized, supercooled gases out into space. The jets are cold because their source is not a sun-warmed surface, but a deep internal refrigeration cycle. The bizarre chemical signature of the plumes, rich in noble gases and nitrogen, but poor in water, of course. The hyperclathrate crust is a cage. As the internal pressure cracks it, the trapped gases are the first to escape, blasting outwards before the heavier water ice can even sublimate. And the fluctuating, strangely powerful magnetic field, the model predicted that too. Ferroelectric materials, by their very nature, generate a powerful electric field when their molecular structure is altered. The phase transition rippling through the core of 3I, Atlas, was acting as a colossal dynamo, its constant internal reconfiguration of electric polarity generating the shifting, turbulent magnetic environment we had observed. Every single mystery, every paradox was resolved. The object wasn't breaking the laws of physics. It was demonstrating a deeper, stranger, more beautiful application of them. It was a natural, self-regulating heat pump, a celestial engine running in reverse. The sun's energy, which should have been its executioner, was paradoxically being used as fuel for its own preservation. The more heat the sun poured onto it, the more efficiently the internal engine would run, and the colder the surface would become. It was a perfect crystalline feedback loop. A mechanism for survival so ingenious, so counterintuitive, that we could never have conceived of it without first seeing it in action. To confirm this, teams around the world frantically reanalyzed the data, building new computer models based on the Kyoto team's audacious theory. They plugged in the numbers for anisotropic thermal conductivity for a high-pressure endothermic phase transition, and they watched in astonishment. The simulated cooling curve on their screens was a perfect, flawless match for the light curve of 3I, Atlas. The predicted jet velocity, the temperature, the composition, it all aligned. The model worked. It held together. The feeling that rippled through the scientific community was not just relief, but a profound, humbling sense of awe. We had been so focused on what we knew, on the familiar dance of comets and asteroids, that we had failed to imagine what else could be possible. We had looked upon a miracle of alien physics and seen only a chunk of ice, 3I. Atlas was not a comet. It was not an asteroid. It was something entirely new. A new class of object born in the crushing hearts of interstellar nebulae or the catastrophic collapse of ancient protoplanetary disks. A cryodynamic engine, some began to call it, a relic from a process of planet formation we didn't even know existed. The solution to the puzzle of 3I, Atlas, was more fantastic than any of the problems it had presented. It revealed a universe not only stranger than we imagine, but stranger than we times can times imagine. A cosmos where, under the right circumstances, fire can bring ice. Where a journey toward a star can be a journey into the cold. We hadn't just solved the mystery of one strange visitor. We had unlocked a door into a new realm of cosmic possibility, and were left to wonder what other impossible things were now waiting to be discovered in the darkness. What then are we left with in the silent, receding wake of this cosmic ghost? We are left with the echo of a profound scientific disruption, the aftershock of an encounter that fundamentally altered our place in the galactic story. For years we had gazed out from our small, sunlit harbour, scanning the horizon for signs of other shores, imagining the worlds that might lie beyond our sight. We built our theories, our models of how solar systems form, and how their constituent parts behave, all based on the familiar family of objects orbiting our own star. Our comets were dirty snowballs, predictable in their brilliant self-destructive displays of gas and dust as they drew near the sun's warmth. They were ours, born of the same protoplanetary disk as Earth, and we thought we understood their language. Then, from the unimaginable depths of interstellar space, came a messenger that spoke in a tongue we had never heard. 3I Atlas was not merely a visitor, it was a contradiction, a paradox wrapped in a shimmering, ghostly coma that defied the very laws of solar physics we held to be universal. It arrived without fanfare, a faint smear of light against the velvet black, initially indistinguishable from the countless local wanderers that populate our system's outer fringes. But its path, a searing hyperbolic trajectory, told an unambiguous tale of foreign origin. This was a true outsider, a piece of another star's legacy hurled across the void for millions, perhaps billions of years. We watched, expecting a familiar spectacle. We anticipated the sun's fiery breath to work its ancient magic, to sublimate its ices, to peel back its layers in a glorious sunward-facing tale. We prepared our instruments to read the chemical story written in that plume, a story that would tell us of its distant birthplace. And then the impossible happened. As it plunged deeper into the crucible of our inner solar system, as the solar radiation intensified to the level of a celestial blowtorch 3I, Atlas began to grow colder. Its activity, the very source of its faint glow, began to wane, its voice fading to a whisper precisely when it should have been screaming. This single, bewildering observation sent a shockwave through the astronomical community. It was as if we had watched a block of ice refuse to melt in a furnace. The models collapsed. The textbooks with their neat chapters on cometary sublimation and solar heating were rendered incomplete. Here was an object that possessed some unknown mechanism for self-regulation, some bizarre internal architecture, or exotic surface material that could insulate its volatile heart from the overwhelming energy of a star. Was it coated in a porous, almost aerogel-like crust, a perfect insulator forged in the alien conditions of its home system? Did it possess an internal structure that channeled heat away from its core, venting it in ways our instruments were not designed to detect? Or was the answer even more profound, pointing to a composition of matter, a type of ice or rock, that simply behaves differently under thermal stress than anything we have ever encountered? The questions it posed were not incremental. They were foundational, forcing us to admit that our catalogue of cosmic materials was missing entire chapters. The journey of 3I, Atlas, became a frantic global pursuit of understanding. Every telescope that could be trained on its fleeting apparition did so, collecting photons that had travelled for eons, only to fall upon our detectors for a few precious months. These faint signals were forensic evidence from a crime scene billions of kilometres away and millions of years in the past, the violent birth of another solar system. Its survival of that cataclysmic ejection, followed by an immense journey through the radiation-soaked, vacuum-sealed wilderness between the stars, was a testament to a resilience we did not believe possible. An ordinary comet, one of our own, would likely have been eroded, shattered, or baked into an inert husk by such an odyssey. Yet 3I Atlas arrived not as a dead cinder, but as a cryptic active entity. It carried within its frozen core a pristine sample of the ingredients that built worlds around another sun. Its composition, teased out from the faint spectra of its coma, hinted at a stellar nursery vastly different from our own. The isotopic ratios, the subtle variations in the atomic weights of its elements, were like a foreign accent, confirming its exotic origins. These ratios are the fingerprints of a star's formation environment, and the fingerprints of 3I Atlas did not match our sun or any of its children. It told us that the chemical recipe for planetary systems is not universal. Some are richer in heavy elements, others more abundant in certain volatiles. It demonstrated with chilling finality that if we want to understand the true diversity of worlds in the galaxy, we cannot simply study our own backyard. The galaxy is not a monolith. It is a mosaic of countless different environments, each producing its own unique celestial progeny. 3I Atlas was the first physical proof of this principle to ever pass through our hands, a gift from the cosmos that was as informative as it was transient. This object forced us to reimagine the very nature of comets, not as fragile snowballs, but as potentially robust armored vessels. We now have to consider a whole new class of celestial body, one whose existence was only hinted at in the most speculative theories. These are objects built to last, forged in environments that imbue them with an incredible durability. What does this mean for the story of our own planet? We have long theorized that comets from our own outer solar system delivered the water and organic molecules that made life on Earth possible. But if interstellar objects are not only common but also incredibly tough, it opens up a far more tantalizing possibility. It gives new life to the old idea of panspermia, the theory that life itself can travel between the stars. Imagine for a moment the interior of 3I Atlas. Protected by its extraordinary insulating shell, shielded from the sterilizing radiation of deep space and the intense heat of a star's embrace, the conditions within its core could have remained stable for geological timescales. If its parent system harbored life, it is conceivable that microbes, spores, or the complex organic precursors to life could have been blasted into space, frozen within an object just like this one. It could have acted as a cosmic ark, a lifeboat carrying the most tenacious forms of life, or at least its fundamental building blocks across the interstellar ocean. For millions of years, this precious cargo would lie dormant in the frozen dark, waiting for the warmth of a new sun and the welcome of a new watery world. We are not saying that 3I Atlas carried alien microbes. We have no evidence of that. But its very existence, its demonstrated ability to protect its interior from extreme environments, transforms panspermia from a fringe philosophical concept into a physically plausible mechanism. It suggests that the seeds of life might not be isolated phenomena, but a galactic resource shared between star systems over the vast expanse of cosmic time. The thread of biology, not just chemistry, might connect us to worlds we will never see. And so we stand at the threshold of a new era, one that 3I Atlas has single-handedly ushered in. Before its arrival, the discovery of interstellar objects like Oumuamua and Borisov were revolutionary but isolated events. They were anomalies, statistical outliers in our surveys. We now understand they were merely the first drops of a coming rain. The Vera C. Rubin Observatory, now preparing to open its wide, unblinking eye upon the southern sky, will change everything. Its massive mirror and camera will conduct a survey of unprecedented scale, the legacy survey of space and time, scanning the entire visible sky every few nights. It is an instrument built to detect change, to find the things that move and flicker in the dark. It will be the ultimate net for catching these interstellar fish. Where we once discovered one of these visitors every few years, we will soon be finding them every few months, perhaps even more frequently. The trickle of data will become a torrent. We will build a true catalogue of these celestial immigrants, comparing their trajectories, their compositions, their behaviours. We will learn to read their stories, to sort them into families, to understand the astonishing variety of objects that other stellar systems produce and eject. Some, like Borisov, might resemble our own comets, Others may be strange rocky shards like Oumuamua. And some we must now assume will be enigmatic paradoxes like 3i, Atlas forcing us once again to tear up our assumptions and start anew. Each one will be a new piece of the galactic puzzle, a new data point revealing the secret chemistries and violent histories of our stellar neighbours. We will no longer be limited to studying our own solar system to understand planets. We will have samples from 1,000 others delivered directly to our doorstep. This is the ultimate legacy of that cold, silent wanderer. It was more than just a scientific curiosity, it was a profound expansion of our imagination. Before 3i, Atlas, the space between the stars, felt truly empty, a desolate chasm separating isolated islands of light. Now we know it is not an empty void, but a vast dark ocean filled with unseen currents, carrying the forgotten relics of distant creations. We know that the pieces of other worlds are drifting through our own system right now, silent and unseen, carrying with them the untold histories of their birth. The object reminded us of a lesson we must constantly relearn. The universe is not only stranger than we imagine, it is stranger than we can times imagine. Our models, our theories, our most cherished scientific certainties are always provisional, waiting for the next messenger from the dark to arrive and show us how much more there is to learn. It is gone now, hurtling back out into the endless night from whence it came, its trajectory forever altered by its brief gravitational dance with our sun. We will never see it again. Its secrets, the ultimate truth of its composition, and the story of its impossible journey are likely lost to us forever. But it left behind a gift. It left us with a deeper and more humbling appreciation for the sheer boundless creativity of the cosmos. It shattered the comforting familiarity of our own solar system and showed us a galaxy teeming with unimagined possibilities. And it lit a fire of curiosity that will drive the next generation of explorers to cast their nets wider, to look deeper, and to listen more carefully to the silent whispers travelling between the stars. The phantom has receded, but the hunt it inspired has only just begun. Out there, in the infinite black, are more messengers, more paradoxes, more wonders, waiting for their brief moment in the light of our sun, ready to once again redefine our reality.